Good morning, everyone. Welcome back to our 6th session of Virtual EnviroTech. Our next session is a little bit of everything because I lack creativity in trying to name things. So for our next 4 presentations, our moderator is Liesl Hanlon of Think EnviroTechnical, and she'll walk us through the next 4 presentations. And then I'll be back at the end again. So I'll over to you to start and bring up the first presentation. Thank you.
Awesome. Thank you, Joe. Good morning, everybody, and thank you for joining us. Just a couple of housekeeping things. On the sidebar, you'll see an opportunity for you to post questions, and we'll ask those. I'll ask those to the presenter at the end of the presentation. Each presenter will have about 25 minutes to do their presentation, and that will leave us with about 5 minutes for questions. So we'll try and keep this on time as much as possible, but there is the small chance that we'll go over past 1 o'clock. So I will turn this over to Greg.
All right, thank you. Okay, I think I've got my screen shared. So thank you everyone for coming to this. I'm doing the presentation from the office here. My internet at home is a little flaky in and out, so I wanted to at least hopefully have a more reliable bit to you all. So hopefully this stays stable. I'm going to be talking today about the SST version 3 and some of the differences between it and previous version in terms of what has changed for producing more robust guidelines and how all these changes relate to generally more relaxed guidelines and generally lower remediation volumes. So before I get into it, just want to acknowledge Anthony Knopfler as well, basically the creator of the tool, and we've been co-working on this with other people for many years. So he's presenting right after me here. So yeah, if you stick around after this talk, you'll have some other interesting things related to this. Also, would like to acknowledge PTAC. They've been a large funder of this project for the entire time of it since its inception. The federal PERD program was also heavily involved in the SAR aspect of it, which is rolled into the tool now. Alberta Environment and Parks obviously heavily involved on the regulatory review and technical aspects of it, along with Alberta Energy Regulator, and the City of Calgary had some involvement many years ago. The presentation, just as a brief overview, going to just go through a little bit of general information first and the conceptual model for version 3, and then largely focus on key changes to the tool from version 2.5.3. So that will include things like a discussion of the drainage rate and how they've been updated, and then a few of the relevant to the tool. So the root zone, dugout, pathways, aquatic life, DOA. I'll be discussing these pathways in the conceptual model, how sub areas work now, some other features that have been added, and then also get into the SAR and sodium guidelines, which is a new feature added to the tool, obviously. So the conceptual model there, and just a very brief little study of some example calculations. And then a bit of information on the certification course as well. So the tool, as most of you are aware of, it allows generation of tier 2 subsoil chloride guidelines for below the root zone. So whenever I talk about subsoil in this context here, we're always talking about deeper than 1.5 meters. So it's different than the subsoil that's talked about in tier 1 guidelines in different spots. The tool's been around for many years now, more than a decade now, I guess. So the most recent version is getting a bit long in the tooth. It was released in 2014. That's version 2.5.3. Version 3, the one I'm talking about right now, is just in the final review, final edit stage. So its release is imminent. It'll be soon this summer. And really what the tool does is it considers key receptors for salinity to ensure that there's minimal risk, both current day and in the future, to the various important receptors, and that lets remediation activities happen as efficiently and effectively as possible without remediating sites, without under-remediating sites, just to dial it in as accurately and efficiently and fairly as possible. And the chloride version of the tool, it generates guidelines for generally up to 5 standard pathways. If you've used the tool before, you'll be very familiar with these. And it uses a similar process as what's used for the Tier 1 guidelines in terms of each pathway is evaluated independently, and then the most constraining pathway is essentially what drives the remediation for the site or for that sub-area of the site. So these 5 pathways, they are the root zone pathways. So always implied in the tool, if you're using the tool and cleaning up a site using an SST assessment, it's always assumed that the root zone, the top 1.5 meters, is being remediated to Tier 1 guidelines for both EC and SAR. That's sort of the line in the sand where things are linked back to Tier 1 guidelines. So to make sure the root zone, kind of the prime agriculturally productive zone, is kept sufficiently productive, it needs to meet Tier 1 guidelines. And then what the tool does is it lets you switch from EC and SAR on a Tier 1 basis to chloride and sodium and SAR on a Tier 2 basis in subsoil below the root zone. So these 5 pathways for chloride, they're similar to the ones that are used for sodium, but they're a little bit different. So for chloride, there's the root zone pathway, which is essentially referring to upward transport into the root zone. The root zone today, so right after any sort of remediation happens, it basically requires that the root zone is current time meeting Tier 1 guidelines, and then this pathway for the SST ensures that it meets Tier 1 guidelines in the future as well from this potential upward transport of chloride into the root zone. Livestock watering and irrigation are both dugout related pathways related to water, which is impacted with chloride and or sodium leaching into a hypothetical future dugout that might be put in the impacted area. So those are highly related pathways and mainly relevant to agricultural land. Aquatic life is relevant to any kind of land use, and that is obviously relevant to impacts where they are today, which presumably aren't, or hopefully aren't, near an aquatic life receptor, and taking care of the potential for them to be transported through groundwater towards a receptor in the future. And a similar thing for the domestic use aquifer pathway. The presumption is that a DUA, a source of drinking water, isn't contaminated today with chloride, but the tool ensures that in the future it also stays adequately protected. So these 5 pathways are the same for both version 253 and version 3. So it's just differences in how the 5 pathways are handled for chloride that makes a big difference. And site by site, the pathway that constrains the most, it can't really be predicted. It's a function of many factors like soil properties and groundwater properties, nearby receptors like aquatic life and the DUA. So it really is a very site-specific approach, which you would expect for anything Tier 2 related. This diagram here is just a very simple schematic of these 5 receptors for the initial chloride or sodium SAR impacts. There's upward migration into the root zone. There is leaching into a dugout where it can be consumed either by livestock or used for irrigation. There's downwards leaching towards a domestic use aquifer, and there's also lateral transport towards an aquatic life receptor. So those are the 5 basic pathways considered both in the previous versions of the tool and the current one. So the current one, meaning the old one, version 253, here's an example of the input page for it. And this is kind of the last input page. And I show this one because it gives an example of one of the limitations of version 253 in that it can only handle 1 sub-area at a time. We'll get more into that later, but sub-areas are a very important assessment tool in terms of dividing a site into different impact zones or different source areas to allow guidelines to be made more robust and remediation volumes reduced. So to be able to use sub areas efficiently is a key thing, and version 3 is much better at that than version 2.5.3. Version 2.5.3, you can give some very limited information about sub areas, but for the most part, it's doing one area at a time. You can only describe the top and bottom of impact and the source length, things like backfill qualities for one sub area at a time in version 2.5.3, which works, it's functional, but it has some limitations to it. In version 2.5.3, there's updated protocols and calculations. One of the big things is being able to handle multiple sub areas at once. So I'll show some screenshots of that when we get to it. It's got very expanded capabilities in different areas of the tool. The documentation is updated with much more detail added in many areas. And then of course there's now the SAR and sodium aspect to it. So the tool is one tool still, and essentially there's a split that you can do an assessment either for chloride or only for SAR, or you can do it for both. So by using these two buttons here, you can go down one path or the other and back up and go to the other one. So it gives a lot of flexibility in how sites with some combination of chloride and SAR or sodium impacts are handled. So in terms of some general parameter updates, there are quite a few updates here. Some of the important ones, but easy to describe, are things like chloride impact depths can now go to 15 meters instead of 10. Water table depth can now be described down to 15 meters instead of 10. The maximum DUA depth relaxed to 25 meters instead of 20 meters. And one important thread through this version of the tool is there's been a strong emphasis on harmonization with Tier 1 guidelines. So for instance, fine versus coarse soils is now determined by the sieve analysis rather than hydrometer. And the bulk density and porosity are now harmonized with Tier 1 defaults rather than the previous numbers used for the tool. Another place where the harmonization has happened is hydraulic conductivities, where they are now faster than they were before in terms of defaults for shallow groundwater. So they've been increased to 10 to the -6 for fine and 10 to the -5 for coarse. This would be one of the, I would say, one of the few changes that's more conservative with this version of the tool, making groundwater faster, but it's been offset for in various other ways for different pathways. Drainage rates are more harmonized with Tier 1 now, so you'll see numbers like 12 and 60 millimeters per year more frequently, which jives with Tier 1 better. And as I say, there's a big improvement in the handling of sub areas. So it can do up to 5 areas at once rather than doing them sequentially. And this screenshot here shows an example of that, where you can enter up to 5 sub areas. You can do different source dimensions, different distances to aquatic life receptors, different top and bottom of impacts, different ways the root zone is handled. So it makes it a lot easier to keep track of the site in terms of not needing multiple different files to handle one site. And it also gives a lot more power in terms of being able to calculate guidelines more effectively, because the tool now has more context for your whole site. It's not just got a little window into just one sub area essentially. So in terms of the chloride guidelines, there are a lot of enhancements and expansions for all pathways, and they make them more robust in all cases and refined in many areas. And for the most part, these refinements have allowed removal of various conservative assumptions that would have been present in the previous version of the tool. And this frequently, but not always, but most of the time results in increased guidelines for the various pathways and typically reduced remediation volumes while still maintaining equivalent levels of environmental protection. So some of these updates are very specific to one or two pathways. Some are very high level overarching, and they affect many pathways, like some changes to bulk densities and drainage rates. And there are a couple of other new features that are useful for specific aspects, such as sentinel wells have been added as an option. Drainage rates, they play a very important role in a lot of pathways, basically all of them, and they affect the way in which impacts either discharge upwards or leach downwards towards the water table or towards the domestic use aquifer. And there's now a lot more refinement than there previous was. There's more categories for drainage rates and a lot more complex interplay between texture and climate and vertical gradient. Previously, vertical gradients, when they were present, would just override climate information, and now there's a more refined combination using the three in harmony rather than having one overpower the others. And related to this, there's also a new feature where hydraulic conductivities relevant to drainage rates can be entered, and it fixes a little bit of an issue where vertical gradients on their own only provide kind of limited information about true vertical groundwater flow. You need both hydraulic conductivity and gradient to have a good understanding of how vertical flow works. So having that added adds some extra refinement to the ability to predict drainage rates. So one of these pathways, so the root zone pathway, it results in getting a little bit of feedback here. I'm not sure where that's coming from right now. The root zone pathway, one of the things that has happened for it is that the drainage rate updates affect the root zone pathway in several different ways, largely affecting the rate at which chloride discharges up into the root zone. There's been some changes also with how shallow soils are handled in terms of excavation and backfill properties, which can be dialed in a little bit more, like specifying sat percent. Conservatism in the impacted root zone scenario is reduced now. And one major thing that's just been recently added to the tool is the effect of water table on root zone guidelines has been really looked at in some detail and added in. And it previously wasn't much of an influence, but it's a strong influence now because drier soils with deeper water table are generally less at risk of discharge to the root zone. So that is factored into it now, where deeper water tables, you'll generally find more relaxed root zone guidelines than the shallow water tables, which is generally the assumption that the previous version of the tool would have been using for that pathway. Dugout pathways, there's been improved handling of things like background salinity via a more complex mixing model. One of the big effects of this is it reduces the amount of times that irrigation guidelines are constraining. They used to be highly problematic on a lot of sites. Now it's much less problem for irrigation to be an issue. The guidelines, the final guidelines used are slightly refined compared to what they are before. That's more of an under the hood kind of thing. The final end result of subsoil chloride guidelines on a milligram per kilogram basis are generally more relaxed than they previously were. They're higher, and it's due to one of the big things being a more elaborate mixing model where the mixing into the dugout takes into account more effects like water table depth, climate, hydraulic conductivity, and gradient of shallow groundwater. And this replaces some previous assumptions, which were very, very rough, high-level assumptions of dilution of 3 or 10-fold with something more calculated and robust. Dugout size is assumed to be a little bit deeper than previously, so it won't be as excluded as often, but it also won't be constrained as often. And just some improvements in the guideline in terms of using enhanced mixing models. So again, results in generally higher guidelines for these dugout pathways than previously done. It uses various things like dugout sizing calculations from Alberta Agriculture, uses different evaporation zones from across the province, and again, the net result is generally less remediation being called for irrigation particularly. Aquatic life pathway, many updates to that one. One of the big ones is since coarse soils now have a very fast default hydraulic conductivity, the tool can accommodate faster groundwater velocities up to 25 meters per year. This isn't a very common situation in reality, so this is something the tool would be more dealing under some default conditions, and generally as you characterize a site, these defaults would get replaced with more realistic site-specific data. With Changes in bulk densities, there's different porosities used, so it results in different groundwater velocities, different pore water conversions. And one big thing added to this version 2 is some conservatism removed from some complicated interactions of subareas when they are very close to aquatic receptors. There's been a neural network algorithm included in it that allows reducing some of the extra conservatism that was present in version 2.53, where it was just there due to complexity of the modeling. But now with this more elaborate method using the neural network, we've been able to remove some of that conservatism, which helps increase some of the guidelines appropriately where multiple subareas are relatively near aquatic life receptors. DUA pathway, these intermediate drainage rates, those obviously have a big effect on DUA risk because they affect the rate of salt moving downwards towards the DUA. Pore water conversions are different due to the different bulk densities. And there's a more elaborate mixing into the DUA going on using a flexible Summers model instead of a simple DF3. It's similar in many ways, but the Summers model allows more robust handling of background chloride in multiple subareas. And there have been some other tweaks in the background to allow the improvement of handling of interactions between different subareas also. And a recent thing that was added too is some extra refinement and interpolation in deep groundwater properties for how impacts get laterally smeared out as they move downwards towards the DUA. So there's less rounding or less bucketing, we call it sometimes, of parameters towards more conservative ends. So that also helps guidelines. The Summers mixing model, won't go into it, but it just allows a more robust way of mixing water and chloride fluxes from different areas into the DUA and making sure the DUA stays protected at all points along it. And it also has a better way of handling higher background chloride in the DUA, which doesn't come up very often, but when it does, the current method, the new method Summers, is more accurate and less conservative than the version 253, which gave unnecessarily low guidelines in those situations. The Sentinel well feature, this is a new one, and it allows the assumption of a hypothetical Sentinel well relevant to either aquatic life or agricultural land for dugout pathways if your site is non-agricultural. And you can define the location of these Sentinel wells. And what it does is it provides upper bounds for future groundwater chloride concentrations at those Sentinel wells. So it's mainly useful for risk management and monitoring situations where, especially for sites which might not be getting remediated in the short term and they need to be kind of sat on for a while, but at the same time monitored to see what makes sense with what's known about the site to make sure things don't go out of whack before the site can actually be remediated. So that's it for chloride. The SAR and sodium module. So this is a new addition to version 3. And it allows standardized tier 2 SAR and sodium guidelines to be generated for subsoil. And this is a huge improvement over the previous state where for subsoil SAR, you were limited to essentially either tier 1 as really an unpleasant option often, or tier 2C, which is complicated and takes a lot of data analysis. So this now can be done on a more standardized way. It allows up to 5 areas like subsoil chloride does, and similar pathways, but slightly fewer. It's got a soil structure pathway for SAR. It's also got a root zone pathway, upward migration for sodium, and an irrigation pathway from a dugout, also relevant to sodium. So on this page, you can see the final input page for SAR and sodium. You can define up to 5 sub areas with top and bottom of impact. You can define clay content, background salinity, how the root zone is handled. So it's not overly complicated to do a SAR sodium assessment. It dovetails nicely at the end of information you already need for chloride. The output screen for SAR sodium, very similar to chloride. It gives you guidelines for as many sub areas as you have. It shows the soil structure guideline for SAR and the 2 different sodium guidelines, along with which one is most constraining there. So mentioned already, just briefly go through the 3 pathways. There's soil structure relevant to hydraulic conductivity loss. There's the upward migration into the root zone pathway. It's all about protecting from future root zone SAR exceedances. And the irrigation water pathway, it's to make sure irrigation water doesn't end up too high in SAR and potentially causing a risk by having that sprayed onto sensitive plants. Other pathways are generally considered not really highly risk causing from SAR or sodium, or they're sufficiently protected by chloride. So I won't go over this really in detail, but soil structure, it's kind of a complicated interaction of hydraulic conductivity losses and EC and SAR and texture. But this threshold curves and a bunch of research done in Alberta over many years, they all kind of go into the guideline algorithm kind of behind the scenes and generating a subsoil SAR guideline to protect soil structure dependent on things like background EC. And just as a quick little example of this, say a typical fine grained site, agricultural land, central park land, typical background TDS with some monitoring wells, 4-meter water table, typical shallow groundwater velocity, medium clay content, pretty good background salinity, impacts fairly shallow, like in the top 6 meters, some areas needing some excavation for chloride and tier 1 EC SAR problems in the root zone, some not. With an example like this, when the parameters are put into the tool, it results in just typical subsoil SAR guidelines of say 25 to 29 for this type of site. And those are pretty common. You'll see guidelines higher than that in some cases. You'll see them lower than that in some cases, but that's not an unusual range at all, and very clearly higher than tier 1 guidelines, which makes sense. SAR in subsoil is much less of a risk than SAR in the root zone. So it makes sense that guidelines are much higher than tier 1. And for this example site, it would be saying that no remediation for subsoil SAR is needed once the chloride remediation is done. The root zone pathway, it's all about protecting the root zone from SAR coming upwards and causing problems like hard pan or infiltration loss. It models sodium like it does chloride, but with extra complications due to cation exchange and slower sodium transport. So it does a bunch of modeling runs, comes up with a sodium guideline in a very similar way to coming up with a chloride guideline for that root zone pathway. Irrigation water, again, very similar to how the mixing is handled for chloride now, but instead of looking at EC in the dugout as a final value or TDS, it's now looking at SAR, and it uses a bit of a sliding scale of SAR and EC are interrelated, and it's, again, making sure that whatever irrigation water comes out is suitable for use on plants in the area of this dugout. When doing a site assessment, you think it might go to an SST for SAR, sodium. Mostly it's the same data that you'd need as for chloride. So things like soil texture, good delineation, good background data, maybe vertical gradients, backfill data. Some new things that are needed to make sure you get are, you need better subsoil background information when you're doing SAR and sodium. You would generally want this anyway for chloride, but it's very important for SAR and sodium. And yeah, that's really the main thing. Just make sure you've got good background subsoil data. It gives more context for the SAR sodium assessment. And you also want to be making sure you get clay content data by hydrometer, even though you'll need sieve data now for the overall fine versus coarse. The SAR aspects are really relevant to clay. So you'll want a combination of clay and sieve data. So in general, we've done many case studies on dozens of actual sites, and for the most part, remediating a site for chloride and root zone problems will generally be enough. There'll be some cases where you need to do some extra remediation for SAR or sodium, but a large portion of the time you won't. Soil structure is rarely the problem. Once in a while, irrigation water needs a little bit more remediation for sodium. More often than not, if there is some remediation needed for sodium, it would be due to root zone risk. But again, for the most part, it's really chloride that will generally determine things. And just as an example, that last example that we went through for soil structure, it would correspond to sodium guidelines of about 580 to 2400 for the root zone pathway, which is the constraining one for that example. And in that exact site, it didn't require any extra remediation between or beyond what would have been needed for chloride. So that's really all the information there. And just want to leave it quickly on the certification course. It's a 3.5-day course, looks at SAR and sodium. It'll have an exam like it normally does. If it passed, it allows you to get an SST certificate to be able to submit assessments. If you're previously certified, you do not have to be recertified. We have a little 1-day update course that's optional for that. And dates are to be announced for this. They'll be set very quickly as soon as the final release happens. And these next set of courses will be delivered online due to the obvious COVID issues. So it'll make it easier for some people to be able to attend the course without traveling or being anywhere in person. So thank you for watching for this. And if you want information on courses, you can always email this help address and we can keep you posted on when and where they're set up. But as I say, they'll be set up online for the foreseeable future.
Thank you very much, Greg. I don't see any questions yet. So if anybody has any questions, please type them in the question box. We have a couple minutes, but not too long, but I don't see any questions yet. So Greg, I guess you explained everything that everybody needed to know. So awesome.
Okay, got off easily. Thanks so much, everyone.
Thank you. Our next presenter is Anthony Nafla with Equilibrium Environmental. I'm just going to switch presenters here. Just one moment. Joe, I wonder if you can just help me out here quickly.
Give me a second.
I'm just looking for the next.
I got it. Anthony, you should have a message on your screen to share your desktop.
Yeah, I just saw that. Can you hear me?
Yep.
Can you hear me?
Yes, we can.
Okay, so let's give this a shot here. So can you see the presentation now?
Yes, we can. Thank you. Sorry about that, Anthony. I lost
you need to
my
switch to
button.
view.
Yeah, I don't see me there either.
No, you won't see yourself, but this is at the top. There's a tab that says display settings.
All right, got it.
Switch it to swap presenter view.
Okay, did
there
that.
Perfect.
All right, good to go. And so this audio here is good enough? You can hear me there?
Yes, we can hear you. It sounds good.
All right. All right, so this is kind of building upon Greg's presentation there, and it's really some things that we've been learning when we've been doing different remediation programs combined with SST assessments, primarily, not so much the SSRA. And I guess one of the things we found is that, you know, typically you get all your phase 2 data, you do your SST assessment, you figure out what your dig area is, and then you go to remediation, get your closure samples, and then you're done. But what we're finding is there's an entire new, I guess, stage of work when you're using these SST assessments and you're going to the remediation stage, and you're often reassessing your criteria during the course of your dig, sometimes just before your dig, and sometimes you're doing it after your dig as well. And so I kind of wanted to get into that because it's got important implications and it can really make a big difference in terms of the efficiency of your program. So I think everyone's pretty much, for the most part, had lots of exposure to the SST, and it's relatively easy to calculate guidelines. In fact, it's very easy to calculate guidelines. But if you want really good guidelines, that's a more complicated process, and it really can make a big difference in the total volume of your excavation while still being protective of the environment. And really the goal right now is to, remediate as many sites as possible with the resources at hand. So spending a little extra effort to refine your guidelines and your excavation can really be good for our throughput in this province in terms of remediating our legacy contaminated sites. So when your dig is defined by Tier 2A and Tier 2B, and you can use alternate approaches, but it becomes a little more complicated if you want to do major revisions during the process or after the process. That's one of the nice parts about the SST, is because it's a AEP and AER vetted tool. It allows you to go right through to your excavation. You do it professionally, you've taken the course, you got your right confirmatory samples, you close it up and go to reclamation. Whereas if you're going SSRA, you do have to approach the regulators beforehand, show them how you're deviating from conventional methodologies and perhaps their policy, and get their endorsement before you proceed. So a lot of times when you get to the excavation stage, and particularly if it's, say, a smaller impacted site, you don't necessarily have a ton of data, and you're running your SST assessment based on what you know and your contaminant distribution based on what you know. But you can run into tricky situations. So for example, sometimes with a deeper water table, the lateral spreading of the plume can be quite small. It's basically just going straight down. And so literally moving 5 meters over can change your measured concentrations by thousands of parts per million. And you may not realize that until after you started your dig, in which case you're going to need to reassess your guidelines. You can have conditions that change over time too. So if you have a coarse soil and your data is 5 years old, you could have a different situation today. It could be deeper impacts. You can find new impacted areas. That's very common. And so one thing that often helps these assessments is just before you go to dig, you do some pre-drilling work. And you can use that pre-drilling work as part of your closure sampling if you dig right to the exact location of that borehole. And so we found that to be a very effective tool because it also allows us to refine things along the way a lot better. And so you do need additional budget up front, and you do need additional planning and time to get it set up straight. So this is kind of an example scenario here where it was a site with 3 different impact areas. So there was a tank farm over here, and it's got this white boundary, and that's where the heaviest impacts were observed. And then over here you have a overland spill area, and it broke the berm basically and spilled out into this area. And then there was a sump. So I guess the first thing you do is you go do your SST assessment after you do your delineation. We found in the tank farm area, there was concentrations of chloride up to 5,000 parts per million. The impacts were relatively deep. At least the heavier impacted material was down to 7 meters. We didn't get closure until about 10 meters. And you can see that on this vertical profile chart over here. So we have chloride concentrations on the x-axis. We have depth along the y-axis. So this red dashed line, this is our 100 milligram per kilogram chloride delineation criterion. And here's our guideline that we calculated. But anyhow, you can see a lot of these profiles. It drained through the soil, and then it got into a lower permeability material. And so we have concentrations building up to 5,000 parts per million. And then we got closure by 10 meters. So we want to try and reuse low impact material as backfill if we can, because one, it saves on trucking, it saves digging another pit somewhere else to create the backfill source, and perhaps the landowner doesn't need another dugout, or there's no easily or readily available backfill material. It's better for the environment. There's fewer greenhouse gas emissions being released. So there's some real advantages to studying and understanding how you can move materials within your existing excavations. You're not digging a new pit, and you're not creating a landfill and throwing impacted material there. You're digging out where you already have impacts, and you're replacing higher impacted material with lower impacted material. So you're not making the situation worse, you're making it better, but instead of using perfectly clean backfill, you're using slightly impacted material. So in this tank farm, again, we had 5,000 parts per million down to about 7 meters. And then in the overland spill area here, the concentrations were lower. They peaked out at about 2,000 milligram per kilogram, and it was down to a depth of about 2 meters. And then the sump was a separate story. So there's two things we wanted to look at here. One, can we use the non-topsoil depth interval here, because you don't want to be burying topsoil? Can we use that material and put it into the base of the excavation? Because if you look over here again on our guideline chart, we calculated a guideline of about 3,000 milligram per kilogram. This was a tier 2A assessment. And so it showed that basically it was a 7-meter dig that had to be done, which was fairly deep. Tier 2B wasn't going to make a difference on this site. And basically all this heavily impacted material would need to be removed. Well, can we take some low impacted material from the overland spill, this 2,000 milligram per kilogram stuff, and put it down here where there used to be much higher concentrations? And the other thing to look at is within the actual tank farm area itself, if you look at the soils, and you'd want to start below topsoil, so say 0.3 meters to 3 meters, all those concentrations there for the most part are less than 700 milligrams per kilogram. So why would you want to take that to a landfill? Why not instead shuffle that material to a deeper depth, reduce the hauling, reduce the need for extra backfill, and reutilize it as backfill at your site? It's basically a resource. So just throw it in, then you're good to go. No, this is where the reassessments start. And you can potentially do this before you dig, but you might wind up doing it in the middle of your dig. You have to do some calculations, some important calculations. So one is you need to recalculate your guidelines with the SST. Why? Because your top of impact is going to change. And you're going to get new guidelines, and then you have to see if you have to dig a little bit deeper in some areas for everything to match. And you do it iteratively. You can do it for the overland spill impacts, and you can do it for just the overburden impacts, or perhaps a combination of the both. And so essentially what you're doing is and the other comment is that the lower your concentrations are that you're using as backfill material, potentially that allows you to use a greater volume of soil as backfill. And, as Greg was just talking about the subsoil sodium and SAR guidelines, that's something you also have to do as part of this recalculation. You have to recalculate those guidelines as well, so that you know that once you put this slightly impacted material back into that excavation, that no guidelines are being exceeded. And if no guidelines are being exceeded, then it's risk protective and you can go to reclamation. So the other one is volume calculations, and also considering things like side slope, where you have a larger area at the surface and a smaller area at the bottom. And we don't always see that on our excavation diagrams necessarily. You don't always see people putting in the slope, but it's important because it affects your volume. And of course, you're going to have to consider compaction requirements. And then there's the possibility that, say you have this overland spill area and concentrations are up to 2,000, but let's say most of the concentrations are around 1,000 milligram per kilogram, and you just have a few samples that are around 2,000. Well, you could either remove those 2,000s and send them to landfill if you know exactly where they are, or you can just do some mixing, and you start mixing that material to average it out, and then take an upper bound concentration as the other approach. So you could just say, well, you know what? I don't think the mixing is going to work for this particular material due to weather or various other factors. We're just going to take an upper bound percentile of this impacted material, 95th percentile maximum, and then put that back into the pit, basically. So there could be advantages to mixing, but there can also be drawbacks as well. And you're not mixing in clean soil with that backfill material. You're just mixing that impacted material itself to average out those concentrations. So this is the kind of thing that you get at the end of the day. So on the left, here's the same chart that we had before with our chloride concentrations in our tank farm. And this is our previous guideline here, 3,000 milligram per kilogram. But on the right, this is what things look like now. So this overland spill soils starts at about 2.5 meters, and actually this box should really extend down to 7 meters. And you can see here that everything's capping out at around 2,000, because that's kind of like the maximum concentration that was present in the overland spill area. So all that material has actually been backfilled from 2.5 meters-ish down to 7 meters. Now, if you look at this borehole here, it had higher concentrations. It had about 2,500 or 2,400 milligram per kilogram at 7 meters. It's now exceeding your criteria. So you would want to go and excavate that particular area deeper so that all your concentrations are less than 2,000 milligram per kilogram. And then that allows you to use all this additional impact material as backfill, bringing it up to even a higher depth interval of 2.5 meters. And you can do SST assessments at 2 meters and 3 meters and 4 meters, and then regress them and find what your 2.5 meter excavation criteria would be. And so this has allowed us to avoid sending that material to landfill. And we know that because it's below guidelines across the board, that it does not represent an unacceptable risk scenario. And so when you do your SST assessment, when you're redoing it, you're not entering your top of impact here at 7 meters, which you did before. You're rerunning it, and now you're entering, like I said, 2 meters, 3 meters, 4 meters, and then regressing to see your 2.5 meter guideline, and you're using an impact thickness from 2.5 meters down to 10 meters. And if you don't do this, it's obviously invalid because you can't apply this 3,000 milligram per kilogram guideline throughout such a larger depth interval, because that invalidates the conceptual model. So cost implications. So we reduced our volumes by approximately 35%. It was about an 800K dig-ish in total. So our landfill, backfilling, and trucking costs, we figured we saved around 220K plus or minus. However, your costs, you don't just get all that back because there's a bunch of sources of increased costs. So one, you got a lot more material handling here. You got waste segregation, trucking routes are more expensive. So you need a larger workspace where you pull back the topsoil and potentially more landowner damages reimbursement because of loss of crop area. Material handling is a big one, and you got to be really on your game with this one. It's for accessing it at different stages of the excavation. Tracking is so important. You need an efficient workspace. If you're going to do mixing, you need that occurring in a very specific area. You're going to have more analytical costs, because if you do go to a bit of a mix of this low impact backfill material, how do you know you still don't have a bunch of peaks left? And so you're going to have to do an extensive sampling program so that you can provide a burden of proof that yes, indeed, this remixed soil doesn't have these peaky concentrations. And if you just want a safe, easy way to go, just take the maximum. And then you don't have to get into these issues of mixing and additional analytical costs and perhaps some uncertainty that you may have some high hotspot areas still in that material. And the other one is upfront consulting costs. So there's no doubt you're doing more iterative scenarios, you're revising your SRGs, etc. So with the additional backhoe work and movement work and everything else like that, we figured there was about $60,000 that got spent in addition to where we were. So it kind of takes away from your 220K in savings, so to speak. So we're sitting somewhere on this site around 160K in savings, and that's 20% of the project total. Your percentage is not going to be consistent. It's going to depend on how you can segregate your materials. It's going to depend on access. It's going to depend on the concentrations. There's so many factors that feed into it, but it's not unreasonable that you could get 20% if you did it right for a lot of different sites. And you'll know ahead of time when you do some preliminary analyses. And that was really why we went this way, because we actually did those preliminary analyses to see whether it was possible and whether there would be any savings doing that. And there was a lot of, we did not do this perfectly. There was lots of room for improvement on this in efficiency for sure. So I think that the percent savings could even be higher if it was done really well, perfectly. And so I guess the other thing is backfill sources. So this is really important, and especially if you're in a situation where you have a site and you have a diversity of background environments, and you have to really, your backfill is tricky because you need to meet conditions of, you have to have good access to it. There's the cost. There's the volume that you need, there's the texture that you need, there's the salinity requirements. You got to watch out for other contaminants, metals, perhaps petroleum hydrocarbons, who knows. So there's a lot of effort, as everyone knows, that goes into getting good backfill material. But if you do your SST assessment and you analyze the depth and area that you need beforehand, and then look at some things like situations where perhaps you can use different, I wouldn't say quality, but different salinity levels of your backfill material at different depths and different areas, it can actually make it a lot easier to find the backfill material that you need. And you may even wind up segregating your backfill material in the same way that you might do with your impacted site. So as an example, this is kind of like a hypothetical diagram, but it mirrors the site that we worked on in Alberta. There was this red plume here over to the right. This was our impact area from our source, and it kind of spread around this wetland area, and it moved actually into a different sulfate environment. And so on the left here, we see a vertical profile chart showing sulfate concentrations and depth interval. And this isn't all the data, obviously, but you can see there's two general clusters of data. There's this low sulfate environment and this high sulfate environment. So over in this high sulfate environment area here, you can use backfill material that has higher sulfate concentrations. Because it's more in alignment with your background, and you want to make sure of that. You know, you don't want to be putting, if your background here is 3,000 and your backfill's 10,000 sulfate, you don't want to be doing that. But you want to be close to your background scenario in terms of chemistry so that you're putting like into like. And so by doing this, when we found our backfill source, it actually did have an area, well, 2 of the grids had low sulfate concentrations and the other 6 had high sulfate concentrations. So instead of just saying, oh boy, we're not going to be able to use it because, you know, we got such a low sulfate environment here and we need low EC and SAR, basically we could segregate our backfill material into a high sulfate pile and a low sulfate pile and use it in different spatial areas. And again, tying back to Greg's presentation there, you have to keep track of not just your subsoil sulfate now and EC, you're also watching out for your SAR and you're also watching out for your sodium. And you don't just have to do this spatially, you can also do this vertically. And perhaps in some cases, you might be using 2 different sulfate sources. So sorry, just stepping back a minute. Here from this one particular area, we had 2 distinct sulfate environments because we needed some low sulfate material for the low sulfate area. But if you just find limited volumes of this, you might be looking in 2 different locations. So you could have 2 different sources potentially. And it just makes it a lot easier, especially for your SAR sodium guideline if you have low background chemistry. So again, you can do this vertically as well. So here we have the same 2 groupings of sulfate concentrations, but let's say that you're in an area where you have good soil quality, and your risk is being driven by your root zone. You're going to want to use this low salinity backfill material. But if you get to a certain depth, maybe it's okay to use some of the higher sulfate material, but you kind of would need to do a sulfate risk assessment. And believe it or not, you can actually use the SST to do a boron risk assessment. You can use it to do a sulfate risk assessment. You can even, way back in the day, we were using 253 to do sodium guidelines. And you have to do some calculations outside of the SST, but basically you're using all the modeling effort and you're assuming sulfate moves like chloride or boron moves like chloride, and you can actually derive guidelines for it. And like I said, you have to do some post modifications in Excel because the sulfate guidelines are different for different receptors of concern. But you could actually determine if there was a sulfate risk associated with that backfill material and potentially use it if you're stuck in a situation where you can't get this good low EC salinity material that'll cover all of your excavation. And so there are some cost benefits there. There's some costs on the upfront side and the additional investigations, but a lot of times the backfill EC can drive your excavation depth. So you can have a lot of savings that counteract that. So we're going to do some more presentations of this type of material and these types of quirks that's going into an FAQ for the SST. So people will be able to log on there and you can upload questions, what do I do in this situation, and maybe get some guidance, and it'll be a community type approach. So different people will feed in with different ideas, and the goal is for the general user proficiency in terms of implementation to increase when using the SST and doing these remediation scenarios. And I'm sure we'll learn a lot too in the process. So that's about all I had. We got about 6 minutes left. I'm not sure if there's any questions there.
Thanks, Anthony. I don't see any questions for this particular segment. There was still a leftover question from the last one. I don't know if Greg is around or if Anthony can answer this. It's how long is the certification good for? And I'm assuming he was talking about the certification that Greg mentioned at the end of his presentation.
Greg, are you there?
Okay. Go ahead, Anthony.
Yeah, basically it's as long as you're standing, they're valid.
Okay. Are there any other questions for Anthony at this point? I don't see any posted yet. We've got a couple minutes for questions. No? Okay. Anthony, thank you very much for that. I appreciate it. Oh, here comes one. If your chloride impacts are within 50 meters of a wetland, are you using tier 2C for soil impacts within 50 meters and SST for greater than 50 meters from wetland?
That partly depends on the size of your impact, but generally speaking, when you're within 50 meters of a receptor of concern, like a wetland, you should be moving into a tier 2C type scenario. The SST has some acceptable boundaries in terms of offset between the edge of your impact and your wetland. And one other thing to keep in mind is with the new tier 1 criteria as well, if you're in close proximity to a wetland, you're not delineating to 100 milligram per kilogram chloride. You're delineating to something more like 120 milligram per liter on a saturated paste basis. So it's just important to keep in mind for those scenarios when you're close to a wetland.
Okay, I think that was the last one. Thank you very much. We'll move on to our next presenter, who are Piotr Staniaszek and Randy Rudolph from AECOM. I'm just going to switch over here. Piotr, are we going to share your screen, or are we sharing Randy's?
My screen, but Randy will be starting.
Okay, so we'll put your screen on there, Piotr, and you've got till about 12:25, I guess, and then we'll have some more questions.
Great, thanks very much. So Piotr and I are going to be ping-ponging this presentation, and I think the way that we'll work at this time is that I'll try and start a sentence, and then Piotr will end it. That'll keep things, I think, more interesting. But we're going to be talking about gravel pits and how to improve the results that we get using dispersion modeling. Piotr, just go on to the next slide, and we'll talk about why we're interested in doing this. Some of the key issues around pits. Piotr's going to be talking about some of the best practices that we've seen and contributed to development in modeling pit emissions. And then we're going to be talking a bit about how the techniques that are available to improve the accuracy of dust predictions. And we'll see in the next slide why that's important. And then we'll talk about ways to mitigate, and there's some interesting ways of doing that as well. Yeah, go on to the next slide, thanks. So this is a map of West, at least it was a map of West Calgary. Yeah, just go back for a second. So this is the area that's looking at the western part of the new ring road development. Just COP is just in the northeast corner of the map, and this indicates why gravel pits can often have a high priority among residents. This pit is a new pit developed to support the construction of the road. You see sort of normal or higher residential area just a kilometer or so to the east of the pit, and then country residential on on the pit boundary on the west side. So these are relatively high volume production pits that can have an impact on neighboring communities. Let's go on to the next one, Piotr. Thanks. So really, what are the issues around pits? And we're going to be talking about air quality issues, but they aren't necessarily top of mind. I know that for many pits that we've worked on, traffic is actually the #1 issue because of the increased haul traffic on local roads. The roads may not be built to accommodate the heavier vehicles nor the number of vehicles. So there are safety concerns around that. And if haul vehicles are actually used in the pit itself, of course, they are typically the highest source of dust within the operations. So associated with the dust, one can also have silica issues, odor issues, perhaps if there's a great deal of diesel emission, or if we have asphalt plants that are associated with the pit as well. Noise is always a concern, and again, depending on where the pit is, impacts to surface and groundwater or wetlands can also be a major concern. So there are a number of things wrapped up in these kinds of developments, which are, again, often near markets, which are the major cities in the province. Let's go on to the next one. Okay, so what are we going to be talking about here today? We're going to be talking about primarily about dust. Typically in Alberta, we look at a range of dust sizes in our modeling corresponding to regulatory requirements, PM 2.5, the finer particle sizes that we look at, which are most of concern for potential health effects, right through to the larger sort of 30 micron particles that are more associated with nuisance and nuisance dust. So, with the PM on top of the dust issue, the concentrations in air that we need to look at for regulatory purposes, there's also issues around dust settling on cars or windows nearby. There's concerns around the content of silica potentially in the dust as well. And then obviously blasting is also another source of dust, but typically it's an instantaneous source and it doesn't really enter into regulatory 24-hour type calculations very readily. But blasting is a large source of NOx and CO and possibly SO2 as well, depending on the formulation of the explosive. And then diesel emissions also contribute to those same gases. And as I mentioned earlier, asphalt plants can be a source of odor too. Next slide, please. So what are the specific issues? I've already mentioned dust concentrations as being a concern in nearby communities. These communities have also dust deposition concerns, and they can see visible dust in the air as well. And in some places that actually trumps all other concerns. If they see windblown dust, there's a concern that there are other effects that would be associated with the visible plumes. From a community perspective as well, there's usually concerns about silica. What is the concentration of silica in the aggregate material? And what does that concentration look like when it's mixed with background air? And what are the potential impacts on the community as well? From a modeling perspective, the issues that we face as modelers are, excuse me, we're using emission factors from the US EPA. Excuse me for a moment. And these factors have usually been developed for western areas of the country, which are typically drier than Alberta, and they're uncertain as well. Fugitive emissions are very hard to quantify. So there's additional uncertainty in modeling when we're using these things. And then the blasting as well is difficult to estimate the emissions of NOx and SO2 from blast material. Gotcha, I'll turn it over to you while I cough along out here.
Oh, this COVID. Better check yourself. Modeling of gravel pit emissions, that's my specialty. This is another area where I live quite close by to it, and you could see how many big pits are around this area. So, and they are pretty close to the new communities. For modeling, you could see this nice picture of the fire, but in the mountains. But then the similar plumes we could anticipate from the sources going from the surface. And in order to model those releases, we need to have source parameters, which is source location, physical dimensions, how big they are, and mass flow rate. That's very important. This is emission, which Randy mentioned before, that there's some challenge to get those correctly, especially for mining or gravel pit. Also, meteorological conditions in Alberta, we need to use 5 years of data, which is over 43,000 hours, and also terrain elevation surrounding facility. In complex terrain, the flow of the air might be quite complex, and some models are not resembling this flow of the material correctly. What we are looking for is long-term deposition on soil and lakes. That's important for vegetation also. If you put it on the soil, it goes to vegetation. Vegetation could be eaten by people and so on. That there's sometimes for bigger projects, human health risk assessment or vegetation assessment on soil estimate based on our data. Maximum ground level concentration of pollutant, which we could compare to regulatory limits. And we show also isopletes, which are maximum predictions for a given receptor at receptor grid. And in order to have receptor grid, we make this grid like on this picture, where the more dense receptors are close to the sources, and farther away we have less dense receptors. And we toss to this picture also some special receptors that's closest communities or schools or parks, and in this case Walmart, because it's so close to the town. Pattern should correlate to emission sources and should be correct. In this case, have to admit I did this project when I made some mistakes, and in this case you could see this bull's eye on for the dust modeled on the gravel road. Gravel road is a huge emission source of the dust, but in this case long section of the road was modeled, and all these predictions is unreal. It's not correct. If would be divided into smaller pieces, that we make the better predictions. So you need to really know what you are doing and have some experience to avoid such pitfalls like this one. Windblown dust. In many cases, people are modeling windblown dust using average wind speed for the area, which is not the greatest idea according to me, because the highest predictions, those average velocities are very low, and usually the highest predictions of dust around gravel pits are obtained under low wind speeds. It's meteorological conditions where you have a plume of dust going to the areas close to the source. If you have high wind speeds, then the emissions are higher, but then they are going farther away and disperse on the way. So we can model loading of the track emissions as emissions proportional to wind speeds, lower at lowest wind speeds, higher and highest wind speeds. Highest wind speeds are occurring very infrequently. Even in Calgary, people have perception, oh, there's a lot of high wind speeds. No, there's not that lot of high wind speeds, but they are high wind speeds. Wind-generated dust, usually there is a terminal velocity around 5 meters per second on 10 meter high measurement of the tower measuring the wind. Below this velocity, we could assume that there is no emission. Blast modeling. Andy mentioned blast modeling. This is the picture done in toxic orange cloud created for chemical plant explosion or something. People have perception that if there is a blasting, there will be some toxic cloud going to them, and they expect to see it. In one project, they were asking us, will we see this toxic cloud? No, usually for the gravel pits, when there is blasting, the emissions are lower than in mining, and that's not that bad. Blasting occur for a short time, about less than 2 minutes from picture 1 to picture 6, which I've done for blasting of the material at one mine. It occurs once a day, 2 times a week. And how to model it? It's quite difficult. I usually model it for 1 hour a day, every day, because we want to have maximum hourly or maximum daily predictions. And there are quite big uncertainties in emissions. We could do particulate emissions using one equation, using another equation. It's some needs to be work done to make it more realistic for setting used for our specific project. It's not straightforward. Anyhow. Now Randy should jump to that one.
Okay, so one of the concerns, as I mentioned before, is silica. There are 3 types of silica that are considered to have crystalline silica that are considered to have potential health effects: quartz, crystallobite, and tridymite. Ontario has air quality standards for those 3. Alberta doesn't at this stage. But Alberta does have, and the Ontario standard is the concentration or the mass of those 3 forms of silica in PM10 size particles. In Alberta, we do have silica standards for occupational health and safety, but they're based on 4 micron size particles. So the two data sets are not really compatible, and so there's not a whole lot of information transfer between those two, but they do cause some confusion, I guess, potentially. So this photo that I've got here, it says it's from a Montreal highway demolition, but the reason for the watering of the demolition was because of nearby concerns due to the silica content in the material. So yes, it managed dust, but it was managing dust to reduce the silica content in the air. Next slide, please. Okay, we can go to the next slide too. So now we're going to be talking about a few ways of improving models to reduce their level of conservativeness. That's really been, I think, a bugbear of many of the dispersion models that are used in fugitive emission in dust modeling, is because they really tend to over-predict concentrations. Piotr showed his example of that long haul road where the modeling was inappropriate because the sizes of the sources were too large. They should have been more of them and smaller. At the same time, though, even that overestimates concentrations, and there are new algorithms available now that frankly aren't used very often, and we don't use them very often ourselves, where you can actually do a time history of a moving source. Often haul roads are not super busy, and it is possible to isolate the sources and model them individually, and that is it reduces, I forget what the number is, but it reduces concentrations by something like 30%, which is a substantial margin. Next slide, please. We also, typically in modeling, we don't really account well for how vegetation reduces concentrations by trapping or otherwise influencing the flow of a plume through the vegetation. And actually, he and I have a paper coming up, or a presentation coming up for the Air and Waste Management Conference in a couple of weeks on this subject. But there's relatively little information available on how that happens. There's like 2 organizations in the US that actually have studied this a fair amount. One of them has actually worked in Alberta a bit as well in the oil sands, looking at fugitive dust. But what they find is, or what we're finding as well in our comparing those results to our modeling, is that the modeling doesn't really properly account for the effects of vegetation. And measurements show that, just looking at the bottom bullet on the left, that we can get half the plume being depleted within a few tens of meters of dense or tall vegetation. And those kinds of effects we just can't replicate in our modeling. Go ahead, please. So what these 2 organizations have come up with are sort of rule of thumb factors that we occasionally apply in our modeling now to effectively account for this additional plume depletion by vegetation. And so, you know, looking at the top row, if you've got relatively tall trees, you can effectively assume that the entire plume is depleted. What we don't know very well is what the depth of that forest must be before that happens. I think Piotr and I think that it's probably, you know, a few hundred meters before that happens. And we see, you know, many of our pits that we're modeling as well are in larger forested areas than that. Typically, you know, in areas around southern Alberta and around Edmonton, where land is agriculture or it's got scrubby bushes around, a 25% reduction in predicted concentrations is what we would consider applying. Go ahead. So a couple more things here. ways of becoming more accurate, we've mentioned this, the vegetation impact. Another is trapping of larger dust particles within the pit boundary itself. Many of the pits that we work with, especially in the south where the deposits tend to be larger and deeper, there is significant trapping. As this picture can show, there's trapping of the larger dust particles within the boundary of the pit. And there are models like CalPUF that we use frequently don't have that pit, the escape fractions directly in the model. So we apply that ourselves as a means to provide more accurate predictions. Next, Piotr. Is this still me or is this you? This is over to you, Piotr.
And you mentioned about whole road watering. Yeah, I was muted. We collected some studies from AP42 from US EPA materials, and we found out that for this western for the USA, the median watering efficiency is about 80%, and it applies to watering and to chemical suppressants. There's one photo which shows the untreated road, and there is a water tract. And I thought water tract doesn't emit that much of the dust, but I changed my opinion when I made this photo in the whole road in the mine. Other mitigations, there's enclosures of the crushers, breakers, load outs, and even stockpiles could be also enclosed. There are some companies which they are building these domes around them to avoid dust emissions. Watering, we talk about that. Sometimes in gravel pits, they have mist of the water, which is going on the piles. I think our first photo at the beginning of the presentation, it was good photo showing this misting of the piles in real gravel pit. Berms, they build their berms like 6 meter tall berms around the gravel pits, not only that nobody wants to see what they are doing there, but also to help for noise and dust. And it's good if they are well vegetated. It helps a lot for dust abatement, as Randy mentioned in previous slides. We can also replace whole roads by conveyor. Conveyor has almost negligible emissions, even if it's open, it's uncovered, but then whole roads are the biggest emission sources and biggest cause to complaints from the public. Another ways that are not mentioned on this slide, but I could explain to you, if you could see those stockpiles, they are cones, and cones are not that great for wind speed dependent emissions. It's proven that the kidney shape, which are done by stackers, when you spread material over some area, they are much better, and especially if you make a construction that one stockpile is sheltering another stockpile, so the wind is not going to emit that much from the second stockpile because it's sheltered. those are simple things which, if you know, and you could change your operation and you can decrease emissions. One of them is, in case of gravel pits, if you design your operation that way that you strip new area from the soil and overburden in winter when the ground is frozen and doesn't emit that much or covered by snow and the moisture content is higher than normal, then you have lower emissions. And if you make the stripping end of the new pit on the same time when you excavate aggregate, you make emissions much higher. If you separate those two operations, that's much better for environment and for public perspective. Another thing people are considering, there are fences. Fences are great, but for smaller piles. For these big piles which are on the bottom of the diagram, it must be very tall fence, which will be very expensive fence, and to make it around this area, it would be challenging. So some people, they still install the fences, but it's rather public relations stint than real science, because people are thinking, oh, they do something. But real efficiency of the fences is not that great as you could think about. And I should conclude this with summary. The main issues for aggregate pits is traffic, noise, water pollution, odor, dust, and silicon dust. Dispersion modeling, if properly conducted, is a good tool for estimating air conditions, concentrations. Especially when the pit is not already built, you could predict what concentrations could be in the worst cases when it would be operational. Emission factors have a higher degree of uncertainty, and we could make some innovative ways to make them more realistic by using those effects, escape fractions for the deep pits, wind speed dependent emission factors, and we could obtain better results for modeling, or appropriate approaches to the parameterization of the sources, like this long one for the gravel road. It was gravel road. It was too long. If you make it in smaller pieces, it will be much better prediction. Dispersion models tend to overpredict. They are designed to overpredict because they want to have conservative models, conservative approaches, everything conservative. But for more realistic results, we should consider vegetation cover, this particular trapping in deeper aggregate pits, and mitigations measures. And that concludes our presentation, and if there are questions, we are ready to answer. I didn't change the date for conference because Joe told us not to change anything, but we're supposed to give this presentation on April 29. Just to let you know. Thank you.
Thank you very much, Pieter and Randy. I have a couple of questions for you. Question regarding escape fraction. Is it based on the deposition velocity from Stokes' law? In the CalPUF modeling, is it suitable to apply this when the dry-wet deposition switch is on? And then he says further, since the CalPUF deposition uses the same Stokes' law.
Yeah, that's a subject of our paper for ACE, because those factors are very commonly used in gridded models, CMAC and photochemical models. However, some people argue that Karpov model should handle it through proper leaf area index, proper vegetation, introduction to vegetation in the area, and with proper deposition factors. We split our particulates into 9 fractions. We try to make it as realistic as possible. To every fraction have different more realistic properties, and we still couldn't get this 80% to 100% reduction in the forested area. According to our modeling results for coal mine, it would be 35% reduction due to the deposition in the MPOI in the maximum predicted point, and then it goes a little bit up, but it doesn't reach 80%. So that's our finding. Thank you. Good question.
Thank you. And then there's another question for the vegetation control. Will the regulator accept the using of the vegetation control efficiency in the modeling?
Yes, in Alberta we won this battle. However, in BC we started and we never finished this battle. In Alberta they agree with us. In other provinces it needs to be some convincing the people that it works, because they are not that convinced.
But let's say that it's not commonly applied, and it's used on a case-by-case basis.
Thank you very much. I think we're going to move on to the next presentation now. Thank you very much. And next we have the next presenter is going to be Preston Sorensen with Mapera Analytics. And he's going to be speaking about comparative field studies of real-time soil screening techniques for 2 petroleum hydrocarbon sites. I'm going to switch this over to his screen right now. And Preston, I don't think we can hear you. Are you unmuted? You'll have to unmute, Preston. We can't hear you.
There. Can you hear me now?
Yes. Yes.
Yeah. Sorry. I was clicking, but it was saying that I was still muted by the organizer. So there must have been a delay.
There you are. Thank you. Okay.
So all right. Just to begin, I'll say this presentation was actually prepared by Elsa LeMay from EnviroTech, and she was supposed to be giving this presentation, but she is now in the field. So she asked me to deliver it, since Mapera developed some of the sensing technology used in this study, and have been kind of collaborating with EnviroTech for the last year or so. So for this study, there was 2 sites where we used for comparing traditional kind of PID-based field screening approaches for hydrocarbons compared to using near-infrared reflectance spectroscopy. So the first site was in southern Alberta at the Siksika First Nation, east of Calgary, and then another site was done in December of 2019 in Fort McMurray. Both of these sites have involved diesel storage locations, so it was field screening of diesel related contamination under winter conditions for both of these. The Siksika was done in January of that year, and then the Fort McMurray site was done in December. So just as a little bit of a beginning, kind of go over the 2 different instruments. So the first one, the photoionization detector, that I think most of you, I'm sure, are familiar with. But the basics of it are, you've got ultraviolet light irradiates a sample. You've got ions created and a current that's created between two plates. So the intensity of that current then would relate to the amount of ionized molecules passing between those plates. So it works best with ignitable compounds, so your volatile compounds. It is extensively used for hydrocarbon screening throughout Alberta. The second technology is technology that there's been scientific literature for the last, I'd say at least 20 years, if not 30 years, on the use of near-infrared reflectance spectroscopy for measuring carbon or hydrocarbons in soil samples. The fundamentals are that we've got different types of covalent bonds absorb different types of light wavelengths preferentially. And the majority of soil properties will have spectral features, so they absorb specific light wavelengths in the shortwave infrared portion of the electromagnetic spectrum. And this is particularly true for carbon compounds. So carbon-hydrogen bonds will absorb different types of light wavelengths in the shortwave infrared quite strongly. So the overall method with near-infrared reflectance spectroscopy is because the signals you get can be quite complicated and they're non-linearly related to the level of contamination. The kind of three key steps to the process for using these tools for field screening are we've got to collect our sensor data in the field. We then need to process that sensor data using machine learning and advanced data analysis tools, and then run those results through automated data output systems to visualize the results quickly and rapidly to aid with making field decisions quickly. So the first site that I'm going to talk about is the Siksika Public Works site located east of Calgary. So the first phase of this project involved an environmental site assessment that was done in 2017. So site was phase 2 environmental site assessment. Samples were collected at various locations on the site. So we've got some background samples done just to confirm conditions, and then samples were collected near the fueling station to confirm if contamination was present. And I think, like many projects, there was budgetary constraints on the amount of investigation that could be completed, particularly knowing that it was going to be going to excavation. So during this site investigation, this one borehole here had F2 and F3 hydrocarbons present above the relevant guidelines, with the other 3 boreholes near that one that were all below guidelines. So then in January of 2019, we returned to the site in order to complete the remediation activities, and as with field work, which I'm sure many of you are familiar with, field work in southern Alberta in January, right? It can be snow, lots of blowing snow. It was some pretty challenging conditions, but typical for field work at this time of year. But some of those challenges included safety. We've got -25, so how do we making sure that when you're working outside, you're staying warm? You've got frozen ground. To about frozen, the samples were frozen for samples collected to about 4 feet below ground surface, limited daylight restricting operation time. Both the nature of the hydrocarbons, the degraded diesel range petroleum hydrocarbons, and the temperatures reduced volatility of the samples, which all created challenges for detecting the hydrocarbons at the PID. So the initial estimate was put the size of the excavation to be probably about 25 cubic meters. So we started that excavation then in 2019 here, and we quickly found that the contamination actually had spread south, kind of in between where those boreholes had previously been collected, and was larger than expected. So there was plenty of material to collect for samples where We collected soil samples from both the base of the excavation as well as the walls. Samples were scanned, collected in bags, and then those bags were allowed to increase the temperature and allowed given time for volatilization, and were measured with the PID, and then they were measured with the near-infrared screening tool after they were measured with the PID. So we actually didn't get a PID response in any samples, despite there being substantial hydrocarbons present in some of the samples, upwards of 10,000 parts per million. We did send a number of these samples to the lab for confirmation as well, and one of the advantages too of the near infrared is we're able to collect and measure samples quickly. So we're over the course of the couple days that we were on site, we were able to do more than 49 samples in order to detect and guide the excavation in real time. So one of the advantages then from the near infrared screening is being able to generate 3D and 2D visualizations in an automated manner using machine learning processes. So we're able to visualize the extent of the hydrocarbons in 3D and also in 2 dimensions. So we're able to see the extent of the hydrocarbon contamination at different depths. So I've got a series of slides here starting at the extent at 0.5 meters, 1 meter, 1.5 meters. We can see how the concentrations are changing with depth as we kept digging in order to try to make sure we found the floor, the excavation. 2 meters, we're starting to see that, okay, we're getting less lateral spread to the south. And finally, 2.5 meters, plume was at its smallest. And then at 3 meters, we were able to attain closure and get that data in the field to say, okay, we're at the bottom of the excavation, and we're able to send those samples in for lab confirmation at the end of the project, which confirmed that we had obtained closure, both to the south here, as well as at the base of the excavation. So some of the key advantages from this tool was the allowing for field decisions. So we were lucky in the sense, often working out of the back of a truck, but we had a nice Quonset to work out of for this project. So because we're able to generate this data in real time and our PRD was not giving us any of the responses we needed, we're able to then identify the extent of the contamination, identify that it was larger than we expected in the initial assessment, and then kind of adapt our field decisions and plans accordingly to make sure that we had full closure on the site. You can see some staining here present in this excavation here in this initial, and then as we dug down deeper, we then got below the bottom of the contamination. And here's a visual of the full extent of the excavation with the drone collected. So we were able to get lateral or vertical delineation in this north part of the excavation sooner. So then we were able to bench the excavation and save both excavation time, but also reduce the amount of digging that we were doing on site because we had confirmation that we had obtained closure sooner in this north part, which had corresponded to where that contaminated borehole had been drilled previously. So our initial, if you look at the data from the initial assessment, we've had this borehole was the one that we'd found the contamination, but it actually wasn't the location where we had the highest concentrations, and it was kind of on the edge of the plume. And so we'd seen the plume actually kind of snuck in between just east of this point here, and it extended quite a bit further than had initially been estimated. So rather than being 25 cubic meters, it ended up being about 175 cubic meters of material that we ended up excavating from the site compared to what was initially estimated. So I think some of the key things out of this project was that including the site setup and line locating and all those things. The project was completed in 5 days total. And one of the big advantages, so we were working with, this was a federal funded site. So being able to collect the data in the field and show that to the federal government staff that was responsible for approving the site budget was instrumental, because we were able to send figures and data and get approval while we were on site to amend the budget so we could complete the project, particularly because considering federally funded projects, you know, it can be difficult to get funding for approval to get back out there. So it was great to see that we were able to show to the regulator or to the agency responsible for funding this cleanup the extent of the contamination, and then overall saving money by preventing removes to and from the site if we'd had to wait for budget approval to continue the cleanup. So the second site was a larger facility in near Fort McMurray that had a number of fuel storage locations on site over its site history. So this is just an aerial image of the site. You can see that this was prior to decommissioning and removal of all the on-site infrastructure, but there were a number of fuel storage tanks. Again, diesel was the primary contaminant of concern on this site, and what we had found was that there was extensive site or staining and diesel contamination on the site. One of the things there, we ended up having to do a number of investigation locations, and a lot of, I guess the advantage of having that real-time data again was being able to sort of adapt our drilling plan as we investigated the site to make sure that we could get closure as much as possible. Again, on this site, there was drilling restrictions as normal based on infrastructure and based on getting approval for off-site drilling. So we weren't necessarily able to obtain full closure of the site, but we were able to then adapt our drilling plans and get a much better idea by having that real-time data. So we collected a lot more data than this. I just selected this as a subset. So again, our PID results, unlike the site at Sixica, we were actually able to get, we were getting some PID responses, but they were not really consistent with hydrocarbons that were present on the site. Overall, the near-infrared reflectance spectroscopy, our combined false positive, false negative rate on this site was about 5%. Just to be clear, when we initially go into a site with the near-infrared, the results are semi-quantitative, so we can get an idea about the relative amounts of concentrations at different locations. But we are then, once we get some lab data from the site, able to update our models to make them fully quantitative, so we can generate a quantitative data set for the entire site. But that's, for example, why our F2s are still a little elevated, despite the lab coming back lower, for example, from the data I'm showing you. In terms of the PID responses that we were getting, so it's a little tougher with PIDs because it's not like we can say, okay, for sure if we're above a certain concentration, then we know for sure that that's going to be contaminated or not. It can depend on a lot of factors, but the figure I'm showing you here is a box plot. I'm not sure if you're familiar with it, but I'll kind of walk you through. So what I have on the Y column is the PID response in parts per million for the samples that were collected, and then that had lab data associated with them. And then on the Y-axis here, I've got two box plots. The one on the left here is where there was no elevated petroleum hydrocarbons present relative to guidelines, and Y would be samples where there were elevated petroleum hydrocarbons present relative to guidelines. So the key things, the dots here are showing when we're above the 75th percentile for the data. This whisker here is, or sorry, the 90th percentile. This is the 75th percentile for the data, the median, the 25th, and the 10th percentile. So what these plots show you is the range of values. The key kind of takeaway is that the median response in parts per million amongst the contaminated and the contaminated samples and the non-contaminated samples were actually quite comparable. They almost exactly the same, but actually the non-contaminated samples actually had a slightly higher PID response than the contaminated. And that's actually the majority of the higher values actually were associated with non-contaminated samples. So on this site that had weathered diesel, we actually found where we were getting a PID response, unlike the samples at Siksika where we were not getting a PID response for any sample. There was actually, what this data is showing us is that there is no real relationship on this diesel site between the PID response and whether there was contamination present. This isn't to say a PID is never going to work, right? Again, it comes back to if you're talking about a sample with volatiles, especially fresh volatiles, that's a different story. But on these two sites, they are both weathered diesel and winter conditions, and those two things combined created kind of the perfect conditions to get the poor PID response. So it really, I think it highlights, you've got to make sure you're selecting the right screening tool for the job, depending on the contaminant in question. And the PID is definitely not the right tool for every job. So we found extensive contamination across the site. So the main things, can't really see the numbers, but there's a range of concentrations that we confirmed with lab samples. With the red dots being samples that had elevated petroleum hydrocarbons. And the kind of key takeaways from having this, the near infrared reflectance spectroscopy available, is that we are able to kind of adapt our drilling plans and making sure we investigated kind of every potential source of contamination and staining on the site and get a real accurate and full inventory of the contamination and liability that was present. So again, kind of the key takeaways, adaptive drilling plan in the field for the environmental site investigation was very helpful for making sure that we fully characterized the contamination present on the site. We were able to identify and confirm elevated hydrocarbons were much more widespread than was initially expected on this site. And I guess the other kind of note is from both of these studies, to kind of summarize, is that when you're talking about whether diesel or those heavier end contaminants, and particularly when it's, colder conditions, it can be, the PID, at least for these two, we got very poor results from the PID as a screening tool. And, the other comment I want to make is even, we did allow the samples to warm up and give them time for the hydrocarbons to volatilize into the head space. But that also is a huge time sink when you're talking about collecting samples in the winter. So again, Elsa was the one who prepared this presentation, and they, EnviroSearch had completed these two field trials, which we're definitely grateful for their work. So I've included EnviroSearch's contact information. I'm happy to answer any questions about the project. But also, if you're looking for more information about these two projects, then Elsa would be another person you could contact.
Awesome. Thank you very much, Preston. We just have one question for now. How is NERS on heavy hydrocarbons like F3 and F4?
Yeah, and actually, we get better results for the heavier it in because their larger molecules give a stronger signal. So that's kind of the optimal conditions to use it.
I don't think we have any more questions unless somebody wants to type something real quick. We've got a few more minutes left. Well, in that case, I'd like to thank everybody, the presenters, as well as everybody who took some time out of their day today to join us. And hopefully we all learned something new and interesting today. And enjoy the rest of the conference. And I personally am looking forward to seeing everybody in person very soon. Hey, Joe?
So am I. Trust me. So yeah, thank you, Liesl. Thank you, everybody, for participating in this session. We're going to take a little break, and then we'll be back with our last session. So thank you again to everyone, and thank you to our sponsors. See you back here online in a bit. Thank you.